Okay, so we have a lot of little details, but nothing too hard, kind of fun stuff, lots of pictures. It shouldn't take too long. But what I want to start it out with is working out your quizzes. So let's play around with the quiz. Okay, so here's your quiz. Let's look at question 1. Find parametric equations for the line that passes through the points 4, 1, -2 and 1, 3, 0. So that's what we need to do. And hopefully you remember, and I like to just remember the standard equation of a line, y equals mx plus b, but let's think about it in 3 dimensions instead of just x and y, and we want parametric equations. So instead of y equals mx plus b, we're going to have the vector. Instead of y, it'll be x, y, z. Is equal to, I'm going to write, we'll keep it as m, but m now is going to be the change from the first point to the second point. And then it's not mx plus b because we've kind of already used x when we have x, y, z. It'll be mt plus b, and b is going to be an initial point instead of the initial x value. So that's what we did last time, and hopefully you remember. So now let's write it out. So we have x, y, z is equal to m. Well, m is, again, it's a change. You just take the second minus the first as a vector, and that's 1 minus 4, comma, 3 minus 1, comma, 0 minus -2. Oops. And then times t plus b, and b is just 4, 1, -2. Any questions so far? Okay, now we can put this together, make it look like parametric equation instead of a vector equation, and you can say x of t is equal to, and now we just look at the first component. So we have 1 minus 4 is -3, so we get -3t plus 4, because that's the b for the x component. Y of t is equal to, now we look at the y component. That's 3 minus 1, which is 2t plus 1. And then we look at the z component, and we get z is equal to, and the z component, we have 0 minus -2, that's just 2t, and then minus 2. Any questions at all on the first question?
Does it always have to be written out like that, the x of t -3 plus 4, or is it counted as a parametric equation if it's left as the one above?
The one above turns out to be called a vector equation. The one below is called a parametric equation. So technically, the bottom one is the correct answer for parametric equations. Okay, I probably wouldn't take off a point if you had it, if you had the second line, but just technically it's x of t, y of t, z. Oops, I forgot of t on the z. Does that make sense? That's just language, I guess. It's not like math to learn, it's just words. So again, the middle one is a vector equation, the bottom one is parametric equations, and there's also symmetric equations. I decided not to quiz you on that because that's less important. Okay, let's look at question 2. Find the equation of the plane that contains the points 2, 3, 5, -1, 2, 1, and -2, 0, 4. So on this one, what we need to do is remember the equation of a plane, let me just write this out, is that n dotted with So if you remember, you take the normal vector, you dot it with x minus x naught, y minus y naught, and z minus z naught. And in terms of how the equation works, if you dot those two things, what do you get? If it's the equation of a plane. I think this is easy. So what's that equal to? Yeah, that's equal to 0. Okay, we did that 3 days ago. That's kind of the standard equation for the equation of the plane, or standard form for the equation of the plane. So now we got to go and we have to find n and x naught, y naught, z naught. X naught, y naught, z naught is any of the 3 points, but n we got to do some work on. How do you find the vector n? Vector. Who remembers how you do that? Yeah, what we do is we take displacement vectors, any two distinct pairs will work, and then take the cross product of those displacement vectors. So we could take the first two, and we can go -1 minus 2 is -3. And then we can do 2 minus 3 is -1. We do 1 minus 5 is -4. And then we can cross that with, and we can take the second two if you want. -2 minus -1 is -1. And then we have 0 minus 2 is -2. And then we have 4 minus 1 is 3. Let me write, that was n. Any questions on how I got the two displacement vectors? Any questions on that? Okay, now you have to remember how to cross product. So let's do it. So we're going to go I, J, K. Then we're going to have -3, -1, -4. Okay, and I'm going to do a little trick, and I've mentioned this before. I can just do 3, 1, 4. How will that affect the cross product by getting rid of all the negatives? By multiplying by -1. Not quite nothing, actually, but it's a good try. Okay, if I multiply by -1, what it'll do is it'll switch the direction. Okay, definitely not 0. It'll switch if I multiply one of the vectors by -1, it just switches the direction of the cross product, turns it the exact opposite direction. And the idea is that if you're normal to the plane and you flip upside down, you're still normal to the plane. Any questions on that little trick? Okay, and if I want, I can multiply the second one by -1 too, because then there's fewer negatives. 1, 2, -3. And now I put it twice and I'm back to where I started. It's just a little easier. So now we can go and find the coordinates of n. So the I coordinate is going to be -3 minus 8 is -11. So notice I crossed out the first row and the first column, and then I did the diagonals. Then for the j component, remember you're going to have -9, which is +9, and then minus a -4. So that's 13. And then for the k component, same idea. I get 3 times 2 is 6, -1 is 5. Any questions at all on finding the normal vector? Any questions? Okay, now we just put it together. And I can copy and paste that guy. What we're going to do is take n, we're going to dot it with x minus x naught, x minus 2, comma, y minus y naught, which is y minus 3, comma, z minus z naught, which is z minus 5.
Can you scroll down a little bit?
Yeah, equals 0. Okay, now we just take the dot product and we get a negative 11x. Okay, and then we have plus 22. And then we have plus 13y. And then we have minus 39. And then we have plus 5z. And then we have minus 25 is equal to 0. Any questions so far?
Did we have to show doing that final dot product, or could we have used the general equation for a plane with the a times x sub 0 minus, x minus x sub 0 plus b times that sort of equation? Could we just have said we use that, or did we have to use that final dot product?
The problem with the equation you're using, one is it's harder to memorize. The other is it kind of doesn't give you any intuition on what's going on.
Okay.
Whereas if you do n dotted with a vector in the plane equals 0, that's just a definition of the normal vector. Do you see what I mean?
Okay. Yeah.
And there's nothing to memorize. You just have to remember that a normal vector is perpendicular to the plane.
Okay.
Does that make sense?
Yeah, that makes sense.
That's why strongly, because remember for the final exam, if you're trying to memorize something from every day, you're gonna have too much to try and remember. Do you see that?
Yeah. Yeah.
It's much easier to understand than to remember,
That
at least for
makes
most
sense, yeah.
people. So that's my recommendation. Remember, this is just a quiz. Quizzes are low stakes, but exams are high stakes, and that's you got to remember everything. So
Alright.
the less you have to remember, the easier it is to take the exam. Let me
Gotcha.
clean this up a little bit. So we get a negative 11x. I'm just going to put the letters together, and then plus 13y. And then we have plus 5z. And now let's get the number on the other side that's kind of standard. So first thing, 39 and 25 is 64. 64 minus 22 is 42. And that's the answer. Any questions at all on question 2? Any questions? Okay, question 3. Find the angle between the planes. Okay, so we have the plane 2x minus y plus 3z equals 6, and x plus y minus 2z equals 3. I want to find the angle between them. Remember, the definition of angle involved what? What thing that happened last week? What was the definition of an angle? Who remembers? Yeah, but in particular, it did involve the cosine inverse, but involved the dot product.
Dot product of the vectors divided by the magnitude of the vectors
Right.
multiplied by each other.
Yeah, and then you take the cosine inverse.
Yeah.
Okay, so we need to find out what the vectors are. Well, in this case, the vectors are the normal vectors. So the angle between two planes is the same as or defined by the angle between the two normal vectors. So what we need to do is we need to find the normal vectors. So let's call n1 the first normal vector. And the good news is it's really easy to just look at the equation and tell me what the normal vector is. What's the normal vector for the first plane? And the hint is it's really easy to just look at it. You don't do any like hard math or anything. Yeah, it's 2,
Two
negative 1,
1, 3.
Exactly. So it's 2, comma, negative 1, comma, 3. And then N2 is equal to 1, 1, negative 2. So now we just got to find out, we need the dot product, N1 dotted with N2. Well, that's going to be equal to 2 times 1 is 2, plus negative 1 times 1 is negative 1, so now we're at 1. And then plus 3 times negative 2 is negative 6, 1 minus 6 is negative 5. Any questions on the dot product? Okay, we also need to find the magnitude. We need to find the magnitude of N1. And the magnitude of N1 is the square root of the sum of the squares. So 2 squared plus 1 squared plus 3 squared. 2 squared is 4, 1 squared is, now we're at 5, plus 3 squared is 9, 5 and 9 is 14. So let's make a square root out of it. I forgot to put the magnitude of M1. Any questions on that? Okay, so now we're going to find the magnitude of N2. Then you put spaces after that. Okay, we'll just do it. Okay, N2, we got 1 squared plus 1 squared plus 2 squared is, and then take a square root, is going to be the square root of 6. Any questions on that? So the magnitude of N2 is equal to the square root of 6. So then finally, if we want to find the angle, we take theta is the inverse cosine of the dot product over the product of the magnitude. And then, I got my answer back to the equation again. Notice 6 times 14 is 84. So now we go ahead and pop that in. So theta is equal to the inverse cosine and it's the inverse cosine of the fraction there. Yep. Of negative 5 over the square root of 84. And there's the angle between the two planes. Any questions at all on this quiz?
On the homework, I saw that in the formula for how to do this problem, it was supposed to be, the 5 was supposed to be positive because it's in an absolute value. Is that
Or angle?
correct? Or, yeah, it was an angle formula.
Yeah, I saw that too. It's
Said the
supposed to be
absolute
positive.
value of the dot product at the top.
Let me see. Let me think about it. I have to go through the math. It might be an absolute value. I might have missed that. So let's get rid of that negative. I don't think it is an absolute value, but I'll have to look at that. Leave that in because I don't see the absolute value in my head. I know you're not seeing what's in my head right now, but the idea here is that the cosine of theta, the cosine of theta is u dot v over, or sorry, u dot v is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them, right? Yeah. So oh, I know what the problem is. Yeah, that's if you want the acute angle. So that's a good point. So if you can do angle between two planes, a lot of times you mean acute angle. I wouldn't take off a point by that. Because if you have a cosine inverse of a negative, you could get something more than 90 degrees. So that's where it is. I had to go and do the math. So if you get something more than 90 degrees, okay, actually I shouldn't say that, more than pi over 2 radians, then it's not false, but it's probably cleaner to bring it as an acute angle. Does that make sense? Because usually you can think of an angle between two lines as being acute. That's kind of like that, the same idea. You take two lines in a plane, then you usually talk about the acute angle if you're going to be talking about the angle. But if you let it be obtuse, that's fine. It's not wrong. It's just not as clean. Does that make sense? Okay, I want to mention some, I think that's the end of the quiz. But any other questions about the quiz? Okay, I want to mention something that's pretty important, is that I like to think of the quiz as being a good practice for the exam. Okay, it's timed. You are just given some problems. You're not given answers. You don't get to try twice. So if you truly want to make it a good practice, then you should do it like the exam. My recommendation is try to resist the temptation of going to other sources. Okay, even if you have a little extra time, try not to look at the book, try not to watch videos, look at notes or anything like that, because you don't get that on the exam. On Wednesday, you really won't. Okay, how is Wednesday different than all the other quizzes? Yeah, Proctorio. Okay, other than your spelling, perfect. Yeah, so Wednesday's from Proctorio, so it's going to be a good practice. Okay, the other thing I want to warn you about, and I'm going to apologize in advance, is I have never used Proctorio in my life, and I don't think anyone at LTCC, any faculty, any class has ever used it either. So I couldn't even go to my colleagues in Tahoe to find out what works and what doesn't work. I did talk to a few people that were outside our college that have tried. The semester systems, they're giving finals now, and they're in a whole different, they're much farther beyond where we are. Mess of not having classes. What's that?
Oh, sorry, I just had a question.
Uh-huh.
Is there a way to make the previous quizzes available for practice?
Are they not available?
I haven't seen them on any of the modules. Maybe I'm just missing it.
Okay, if not, then I'll look into it after class.
Okay, cool.
They're closed for me, so.
Yeah, everything I've seen is once they're due, then they're just gone.
One of the problems is that these quizzes are Canvas quizzes, which is different than the MyOpenMath quizzes. I don't know if you know there's a difference.
Yeah, I've noticed.
Program, even though you don't see the program happen. So if Canvas allows me to do it, I'm going to open it up. If it doesn't, then it doesn't, but I'll do my best. Yeah, my guess is that you'll be able to see it, but you'll also see your own answers.
Okay.
I don't think it'll make it blank. There's actually no way for me I can't just copy a quiz. It takes a lot of work.
Yeah.
With Canvas. With my math, I can copy. But I want to do these as Canvas quizzes for a few reasons. But let me go back to Proctorio. So I want to give you that huge warning. Wednesday will be a disaster if you don't have a computer. Okay, you need to have a computer. It must have a webcam. Okay, and you must be able to talk. It must be able to hear you. Okay, a webcam and a mic. If it has a webcam, it has a mic. I don't think I've ever seen a computer that only has one. If you don't have one, what should you do? Not cry.
Right.
You're welcome to cry. I mean, we're crying because of coronavirus anyway. Yeah, you can go to the library. Okay, but you can't just walk over to the library because they don't let you do that. But you can make an appointment, and if you let me know, I can, set that for you. But you can make an appointment and get a computer. Okay, it is an absolute requirement because on the exams you have to do it by computer. Okay? And it has to have webcam because we're using Proctorio. That's just a note. Is that the big note is that the exam, we're doing the quiz on Wednesday as like a practice exam in a way. And not practice for 2 hours and lots of stuff like that, but practice as in getting used to Proctorio. And it may not work. Again, I've never used it in my life. I'm following step-by-step instructions, but who knows? I want to let you know a couple more things. You must use a Chrome browser. Okay, not me being mean, that's just one of the Proctorio settings. So if you don't have Chrome on your computer, you need to download it onto your computer. That's free. Okay, if you did get one from the college, then it has Chrome because it's a Chromebook, and obviously Chromebooks have Chrome. If you don't, make sure you have Chrome, and you have to open up the quiz on Wednesday using Chrome. Got it? You're going to be videotaped, recorded. Also, your computer will be locked to only the quiz. So it will not let you open up another tab or anything like that. Okay, it's going to watch you, so you're not going to be able to look at notes and stuff like that. It watches your eyes. It makes sure that you're not talking to someone else, that kind of stuff. So I want to let you know what's happening. And I think it's better to do a test run on a quiz than to hope it works on the exam, where exams is high stakes. Any questions on what's happening on Wednesday with Proctorio? Okay, so don't do your work on paper. You're going to be typing. Okay, and I'm going to work hard to make sure that it can all be done without really horrible typing. Okay, basic typing. Okay, so that's the deal. You can type anything you want on the little screen that you're looking at right now. That's why I kept it up. Okay, so this is a typing thing. Okay. Any questions on what we're going to be looking at? No calculators, but I'm going to make sure you don't need one. So in other words, leave it like when I have the square root of 84 on the bottom with cosine inverse 5 over root 84, don't even try to do that. Talking to yourself is fine. But if you talk to yourself and someone else with a different voice answers, then don't tell me you're dual personality, split personality, okay? So it's going to hear other people talking too, okay? If it hears a baby crying in the background, that's fine, by the way. But you can't have conversations with any adults, got it? Okay, that's the real rule. No conversations with adults. Okay, babies are fine. Okay, so do your best and don't shoot the messenger. There's not a lot I can do. This is the first time I've ever had to do this. Even with my online classes, on my exams, I don't let them take their test at home. They have to go to a proctor, a face-to-face proctor. So we have to do what we have to do, and there's nothing we can do about it. Sorry about that, but it's the way we're doing it. Any questions at all on the quiz? The good news is you don't have to stress a lot on the quiz. The quiz is a practice to get used to it. Okay, because you still have a few weeks for the exam. But it's gonna, it'll watch your eyeballs and all that kind of stuff. Any questions? Okay. So I want to make it another, let's do a happier thing. I know the exam's not happy, but I want to let you know that the college, one of the great things about living in a small town is there are a lot of scholarships. So if you have not already applied for the scholarships, and I mean, if you're a billionaire, don't bother. Let other people get it. But if you're not a billionaire, then you know, or multimillionaire, then you might as well apply to scholarships. Okay, you are, you know, the top students. Okay, you and the second-year calculus students. I want to be fair. You guys are the top students at LTCC, which means you should be able to get scholarships. Okay, so, but you can't let me know at the last minute that you need a letter of recommendation. You got to give me at least a few days. Okay, and I think at end of the month is when the scholarships have to be finished. So we only have like a week or so to let me know. So think about scholarships again. I always love to see although I think we're not going to be having a live scholarship ceremony this year. You still get to check. But still, it's nice when I hear that my students got scholarships. So I always like to hear that. So again, strongly think about applying for scholarships. They're due in 10 days. Okay, there's a little work, but not that much. So that's just a note, is that let me know, send me an email. And like I said, if you're going to apply to our scholarship at LTCC, then there's a form to fill out. You can contact the financial aid office, and then you'll contact me if you want a letter of recommendation from me. And I think you need 2 letters. I'm not sure. I think you need more than 1. And by the way, you can't ask me twice. That doesn't count. You have to get me and another faculty member, basically, or someone else. Any questions? Any questions? Okay, so let's get to lecture, which is going to be a little shorter than usual because it's not that hard. We're in the single section part of the class. We had, 3 days in a row, I think 3 lectures in a row, where we had to go through 2 sections. And this section is beautiful. I think you'll agree. And this is one of those that there's going to be some stuff we'll use computers on, which means I probably won't be able to test you on the midterm on it unless I can figure out how to make that happen. But I'll test you on the other parts. And but the homework, you're tested on to be able to use a computer. So first thing, how many of you know what a cylinder is? What's a cylinder? Let's start there.
It's a shape with a circular top and bottom.
Okay. Oh, I was hoping you'd say that. That turns out to be an example of a cylinder. Okay. It'd be kind of like if I asked, oh, what is a human being? And you said, oh, Bradley. Well, yeah, Bradley, you're a human being, but you're not all human beings. Does that make sense? So when you're thinking about the circular top and bottom, okay, and it turns out there's no top and bottom of a cylinder by definition. Cylinders go forever. That's actually what's called a right circular cylinder. It's a special kind of cylinder. What we want to deal with is any cylinder. It turns out, and this is going to sound really weird, a plane is a cylinder. Okay, that's another example of a cylinder that you've all seen. Okay, so let me explain what a cylinder is. There's a few ways of defining it. And I'm going to define it a little different than the book, but you can go either way. But I like to start with a plane curve. So we could have, say, a curve in the xy plane. That might be a parabola, for example. That could be a circle, could be a line, could be some weird sine curve, could be any kind of curve in a plane now, not XYZ space. Okay, and it doesn't have to be the XY plane, it could be the YZ plane, or it could be some other funky plane. Okay, then a cylinder is the there's only one L maybe in cylinder, is the collection of all lines through points on this plane, on this curve, that are perpendicular to the plane. Any questions? Let me highlight cylinder, because this is the definition of a cylinder. So I should emphasize that that's what I just did. There we go. Any questions on what a cylinder is? Okay, so that's what a cylinder is. And what you're used to is, cylinders that look like this guy. Okay? Good old bottle. Yeah, that kind of cylinder. A can is a cylinder used to. Those are called right circular cylinders. And that's because the curve is a circle. But now we're going to say, in general, a cylinder doesn't have to have, it could be any curve at all. Okay, so we could play around and take a look at some cylinders. Okay, by the way, here's a picture. Are you guys all seeing this? Yeah.
Yeah.
Good. Okay, just want to make sure that I haven't been talking to myself without you seeing what I'm doing. Okay, by the way, here's a picture of a surface. And I wanted to just kind of give you an example without, I'm not going to get into the details of the sucker. That this is, it's a surface. It's pretty crazy, pretty messy. Surfaces don't have to be clean. Kind of cool, isn't it? I just threw some stuff out there. And there's a surface. And what I like about CalcPlot 3D is you can get a surface, you can see it three-dimensionally, you can rotate it, you can even animate it like that. If you tried to do this surface by hand, good luck. I don't think anyone could do that. But let's take a look at a cylinder now. And by the way, for CalcPlot 3D, if you want to do kind of surfaces that we're doing today, you're going to go add graph, and you're going to go implicit surface. And so let's get rid of that one, and let's add a new implicit surface. Let's do an implicit surface. Want that one. So let's do the cylinder that you're all used to. And that is x squared plus y squared equals 1. And there's the cylinder you're used to. Okay. So when I ask you what a cylinder, that's what you thought about, is you felt like that's a cylinder. Any questions on that idea? But you don't have to choose a circle. You could do, say, y equals x squared. Okay, and the way we're going to write it in CalcPlot 3D, instead of y equals x squared, you're going to be looking at y minus x squared equals 0, which is the same thing. And this, again, is not what you're used to when you think about a cylinder, but this is a cylinder. In fact, sometimes we'll call this a parabolic cylinder because the curve is a parabola. Any questions on that? Okay, and this is actually a very important surface because there's a trench. Do y'all agree? It's the shape of a trench. So really important for fluid dynamics, hydrology. And hydrology is one of the jobs you can actually get in Tahoe. Not that many of them, but that's one of them for good, professional jobs. Any questions on this example? And then a cylinder, no problem? Okay. You could do, I don't know, how about sine of x plus cosine of z equals 0. And this one's a bit crazier. Probably want more than 16 because you're not seeing it very well. So how about 50? And it gives you some weird looking stuff. Okay, that's a cylinder. Now, one of the things to note is that here, the plane is not the XY plane now, it's the XZ plane. And then the lines now are going to be parallel to the y-axis instead of the z-axis. And that's still fine, it's still a cylinder. Any questions on that? So you can draw all kinds of cool stuff. Okay, when you make 50, it goes a lot slower. Let's go back to 16. Any questions at all on this idea of a cylinder? Okay, no big deal. They're not that hard to deal with. You can recognize, how do you recognize when you have a cylinder as an equation? Right? As a picture, you know, you see the lines go all parallel to each other and a curve that is a cross-sectional curve. But how do you see like that sine of x plus cosine z equals 0? How do you know that's a cylinder?
Is it trig functions added together equaling 0?
Not quite, because if I did sine of x plus, say, I don't know, tangent of y plus cosine of z equals 0, that's not a cylinder.
It's pretty cool looking though. Is it just specifically sine and cosine then, or?
No, because remember, x squared plus y squared equals 0 is a cylinder too.
Oh.
I mean, sorry, equals 1. No sines and cosines there.
I don't have a clue then.
Okay. The key is there's a missing letter. So if I drop the cosine of z, now I have a cylinder. And now you can see that if we look at it, that these are lines that are going up and down. You see that? Okay. So Victor is saying it's only on the XY plane. Not quite. Look at the picture. That's not only on the XY plane, but the equation only has x and y.
Or x and z, or y and z,
Or x
right?
and z. Has a missing letter.
Okay.
Okay. So the equation is only an equation of 2 variables instead of 3 variables. Any questions on that? Okay, so a cylinder can always be written as an equation of 2 variables. And then because you have a curve in a plane is a 2 variable thing. And then you just take all the parallel lines from there. And the interesting thing, if you have sine of x plus tangent y equals 0, if you don't say it's in 3 dimensions, it's not clear that it's in 3 dimensions. So you actually have to say it's in 3 dimensions. Does that make sense? So if you're using CalcPlot 3D, then we're talking about cylinders. If you're using Desmos, then we're talking about curves. If you did sine of x plus tangent of y equals 0, you just get a curve. You wouldn't get this kind of cool thing, right? Any questions on that? So there's context. So if the context is 3 dimensions, but you only have 2 letters, 2 variables, then you have a cylinder. Any questions at all on this? And you get some cool objects here. We're not done yet. Okay. What we can do is we can say, well, let's look at the XY plane only. Let's look at the XY plane and just see what does it look like when it crosses the XY plane. And then you get a curve. Do you all agree? That curve is called the trace in the XY plane. You can also look at any other plane, like the YZ plane, and you can look at the trace in the YZ plane or in the XZ plane. It turns out that whenever you have a function where there are three variables, even if they're implicitly three variables, you can always talk about the trace, which is now a curve in a plane. Any questions on that? And that's basically a slice. There's not too much to say about traces, other than they're actually really useful for visualizing, especially when you don't have this 3D beautiful thing. Is that the trace is nice, and they're going to be more important for something else. All right, so now I'm going to tell you a little story. And let's see if you can tell me if there's anything wrong with what I'm saying. Okay, there is an ongoing debate recently, okay, probably for a long, long time, not recently, actually almost thousands of years, about what the shape of the Earth is. There's a group of people that think that the Earth is flat. Do you know that? And then there's a group of people that think the Earth is a sphere. You've heard that, right? So I want to tell you something about reality, is that the people who think that the Earth is a sphere are wrong. Do y'all know that?
Yeah, it's like squashed, right? It's not like a sphere because it doesn't have a uniform radius.
Yeah, the Earth is not spherical. The Earth is not spherical. Okay. By the way, it's not flat either. I'm not one of those crazy people. But it's definitely not spherical. And it's not perfectly what we're going to call ellipsoidal, because that's the next curve we want to look at. It's not perfectly ellipsoidal, but if you look from very far away, it is. Okay. It's as good as our eyes are going to be able to handle it. And you all know it's not ellipsoidal because, you know, we live in a mountain. Do you all agree? If it was perfectly ellipsoidal, there would be no mountains and no valleys. It would just be a boring ellipsoidal Earth. And by the way, it would be covered with water. That would be a bummer too, because the human race wouldn't be around, right? There'll only be fish, maybe smart fish, but we're gonna think about it as ellipsoidal, okay? And just to give you an idea, here's another thing that most people don't necessarily know. What is the tallest mountain on Earth? And we're going to define tall by being the height from the center of Earth. What's the tallest peak? What do y'all think?
Everest?
It's not. It's the
Oh,
one
wait.
that's mainly in the ocean.
The Mariana Trench, right?
No, the one in Hawaii is not even close, by the way, just to let you know. Because remember, it's measured from the center of Earth, not measured from the surface of the Earth, but measured from the center of Earth. Okay, so none of you are saying the obvious one that's false. It's not Mount Everest, by the way. Chimborazo? Where's Chimborazo? Haven't heard that one. Okay. So for none of you have gotten it, by the way. Yeah, it's actually Aconcagua. You got the right idea, though. Yeah, Aconcagua. So the idea here is that that's because the Earth is not a sphere, it's an ellipsoid. And what that means is that it bulges out in the center or at the equator, and it doesn't bulge as much in the poles. And let's take a look at what an ellipsoid is. So now I can pop this equation in, and let's do a new one. So an example, and this isn't going to be exactly Earth shape. Earth is it's just messy numbers. I don't want to do messy numbers. But you could have something like x squared plus y squared over 2, that's over 4, plus z squared equals 1. And that is the picture of an ellipsoid. Okay. And again, you know, it's as good as it gets. There aren't really squares involved, but if I made this 50, it'll go a lot slower because then the computer has to handle a lot more calculations. That looks a little better. Okay. By the way, is this the shape of an egg?
Like a
don't
snake
think
egg,
so.
maybe.
Turns out it's not the shape of an egg because, do you remember last quarter?
Isn't it a hyperbolic
Yeah.
trig function?
Yeah, exactly. Eggs are actually hyperbolic trig functions. I'm not going to get into the physics of all that, but trust me on this one. They're approximately hyperbolic trig functions, even though it doesn't look that much different than an egg. Okay, but they're not quite eggs. So this is an ellipsoid, and ellipsoids are they happen. Notice that it's kind of like, you know, it's not really the Earth because the Earth isn't that ellipsoidal. In other words, it doesn't bulge out that much at the equator. It does bulge out though. Okay, and this is an ellipsoid, and you can see that. But I want to talk about, there's a couple ways of looking at ellipsoid. One is the beautiful picture. The hard thing about the beautiful picture is without a computer, they're hard to draw. Do you agree? Okay, I could actually draw an ellipsoid because I have a lot of practice with it, and I'm terrible at art. But unless you're really good at art or you have a lot of practice, you probably won't be able to draw one that well. But you can hopefully use a computer to draw one. But we can also look at the equation. And what we want to do is we want to say, well, what are the traces? What are the traces for this particular surface? And the idea is that if we look at the trace in the XY plane, what you're doing is you're taking the Z and setting it equal to 0 and seeing what you have left as a two-dimensional surface. And if you do that, then you'll notice you get x squared plus y squared over 4 equals 1. Now, that's a curve, not a surface anymore. So what do you call that curve? X squared plus y squared over 4 equals 1. What's the name of that curve?
An ellipse.
That's an ellipse. Okay, so that's the first thing, is that if you look at the trace in the XY plane, you get an ellipse. Any questions on that? If you look at the trace in the YZ plane, that means you get rid of the X. Then we have y squared over 4 plus z squared equals 1. What is that?
The YZ plane form of an ellipse.
Yep, still an ellipse. Still an ellipse. An ellipse is an ellipse. It doesn't matter like what plane it sits in. It's an ellipse is an ellipse. Okay? You can call it a UV plane and you still get an ellipse. Okay. Now what happens if we look at the XZ plane? Get rid of the y. In other words, set y equals 0. Then what do you get?
A unit circle.
Yeah, you get a circle. Okay. So it turns out circles are special cases of ellipses. I don't know if you know that. So like circles are symmetric ellipses. Does that make sense? So this is an ellipse in any direction you look at. Okay. And circles are ellipses, so we can say that. Okay. And oid means three-dimensional. So a little bit of English. When you see OID, that means three-dimensional. So it's a three-dimensional ellipse. In other words, ellipse in all directions. Any questions on that? Okay. Sometimes you think of oid as circular or ellipsoid, as we'll see in a little bit. But at least for this example, it'll work. So it's called an ellipsoid. Okay. What if I took that 4 and made it a 9? Is it still an ellipsoid?
Yeah.
Yeah, that's not going to change, right? I mean, it's going to stretch it out a bit, but you still get an ellipsoid. What if I took the z squared and divided it by 4? Do I still get an ellipsoid?
Yeah.
Yeah, because
Yeah.
take ellipses, you still have an ellipse, right? Any questions on that? What if I got rid of the 4 and the 9? Do I still get an ellipsoid?
No.
Technically, yes, but it's so special no one calls it an ellipsoid. What do you call it? That's one you're all supposed to know before today. Yeah, that's just a
Sphere,
sphere.
yeah.
There's your sphere. Okay, and that's a sphere because now it's symmetric in every direction. Any questions on that? Okay, so a sphere you could think of as a special type of ellipsoid. So ellipsoids, any questions on kind of what we're looking at? What if I took the plus sign and made it a minus sign? Do I still get an ellipsoid if I took that first plus and made it a minus? Okay, now we look at it, and now you should be a little concerned, because if we look at the trace on the xy plane, then we're looking at x squared minus y squared equals 1.
Yeah, it's a hyperbola.
That's a hyperbola, okay? But if you look at the trace in, say, the xz plane, let y be 0, then what do you get?
A circle.
You get a circle. What if you get the trace in the yz plane? Then what do you get?
I'm not sure.
Okay, someone's sure, I bet. I bet someone can tell me.
A hyperbola.
It's hyperbola. Negative y squared plus z squared is 1 is hyperbola. Remember, changing letters, it doesn't matter. If you let it be, if you let y be, if you let z be x, then that's x squared minus y squared is 1. The letters aren't important. Okay, as long as distinct stays distinct. So it's a hyperbola. So notice a hyperbola in 2 of the views, 2 of the traces, and 1 of the trace is a circle. Okay? So what do you think it'll look like? And that's the top one. So let's take a look. Okay, if we were at UC San Diego, you all know what this is. Maybe.
An hourglass?
Yeah, yeah, it kind of, yeah, it looks like an hourglass. There's a nuclear plant that has that shape, by the way. So it kind of looks like an hourglass, and we have a name for it. It's called a hyperboloid of 1 sheet. Okay, so 1 sheet, and here's the reason, is that if we look at this, and if you, let's say you're walking around this thing, and you're at one of the points, can you get to another point without leaving it? Can you get to any other point on the hyperbola without leaving the hyperboloid?
Yes.
Yeah. Okay, no matter where you are, you can get there. That's called connected. Okay, so this is a connected surface. So it's a connected surface, which means it only has 1 sheet. So that means you can do it with like just 1 kind of piece of paper-ish thing. Any questions on this? Okay, so this is an hourglass. I forgot, who's our physics people in this group? Any physics people? I know we have some, you're just being quiet.
Me.
I want to say.
Me, yeah.
Okay, so just a note, because I do physics, I do some like hardcore physics. If you look at Einstein's theory of general relativity, this is often called the light cone. Okay, kind of looks like this. So if you look at how light moves, then this is kind of like how light moves if you have, say, you know, a black hole or anything strong. kind of in the center. Then it'll curve light. And you've probably heard of that, right? I know you haven't had that physics class yet, but eventually you will. And then you'll learn that the equation is the equation of hyperboloid. Any questions on that? I'm not going to get into it if you do anyway, but you can trust me on that. So there's all kinds of different reasons why you care about hyperboloids. Any questions about this hyperboloid? Okay.
Yeah, I have a question. Are the top and bottom ellipses?
In this specific case, they're general ellipses. They're actually circles.
Okay.
Remember, top and bottom mean what we're doing is we're fixing y to be a constant. And if you fix y to be a constant, you get x squared plus z squared equals 1 plus a constant squared, or just a constant.
The circle.
And that's a circle. On the other hand, this doesn't change too much, but if you go x squared over 4 plus y squared plus z squared is 1, will it still be a hyperboloid of one sheet?
Yeah.
The answer is yes. Okay. The shape's a little different, but it's still a hyperboloid of one sheet. Okay. It's just kind of elongated a bit when you do that. Any questions on that? Let's go back to 16. There we go. Any questions on what it looks like? Okay. And remember, you know, this is a computer program. The top and bottom do not get cut off. These keep going forever. Just let you know that. What if I took the plus z squared and made that a minus z squared? Is that gonna, are you still gonna get a hyperboloid of one sheet?
No.
How is it gonna change things?
It'll pinch off in the middle.
Yeah, let's take a look and we're gonna see. We're gonna get something different. And you're gonna see why we called this one a hyperboloid one sheet. Because now, any guess on what we might call this guy?
Hyperboloid of two sheets.
Exactly. There's a hyperboloid of two sheets. Okay. Notice in this case, here, if we look at the XY plane, that means, sorry, if we look at in this case, the YZ plane, that means we set X equals 0, you get no solution. Do you see that? Negative y squared minus z squared is 1, has no solution. So it cuts it, and you get two sheets.
So it's essentially an asymptote. Correct.
There's no asymptote. It's just two split things.
Okay.
Yeah. Yeah, it's not really an asymptote here. It's really just two pieces. Okay, now we say this is not, this surface is not a connected surface. Because if you're on one of them, if you're a point at one of them, you can't get to any point on the surface and stay on the surface. Do you see that? You have to jump. You can't get from one to another. Any questions on that? Okay. So that's a hyperboloid of two sheets. So now we understand what ellipsoids are. We understand what hyperboloids of one sheet and hyperboloids of two sheets are. What if I get rid of the square of z? What's going to happen now?
It's going to be slightly more linear.
Something different is going to happen. It's not just a linear thing. Changed to everything, didn't it? This is called a hyperbolic paraboloid. Because you'll notice now, if we take a trace, say in the YZ plane, then you get z equals y squared minus 1. That's a parabola. Do you see that? But if you take the trace in the xy plane, I get a hyperbola. Do y'all see that? So that makes it a hyperbolic paraboloid because you got a mix of hyperbola and a parabola. By the way, where does this happen? Where have you seen this kind of shape?
The saddle.
Yeah, exactly. Anyone ride horses? Okay, if you ride horses, you're used to this. This is a saddle. Okay, they call it a saddle because if you ride a horse, that's what it looks like. Okay, and yeah, I've ridden lots and lots of horses in my life, and I actually like without a saddle, but if it's a saddle, that's what you get. Okay, so they call this a saddle. We're going to get into this more, but I want to emphasize one piece that we're going to get into more later. Imagine sitting on this saddle, right? It sits on top of a horse, and you're sitting on it. And you look at the bottom of that. Do you see that? Where your butt touches, right? Okay. And if you look at the bottom of that saddle, notice kind of the way I look at it. If you go left and right, that bottom is a minimum. Do you see that? Do y'all see how the bottom is a minimum? But if you go forward and backwards, the bottom is a maximum. So is this a minimum or a maximum? Think in calculus.
It's both.
The answer is neither. Do you know what we call that point? We call it a saddle. Okay, so we use the name saddle for the shape. We also need to use the name saddle for that point because it's a saddle point, because it's the point on a saddle. That's that max min mixy thing. Any questions on that? Okay, so that is something very different. Now, what if I change this a little bit? And instead of a minus y squared, what if I made that a plus y squared? How is that going to change things? Before I hit enter. Yeah, so now we're not going to get a hyperbola anymore. We're going to get an ellipse in the xy plane. Do you see that? But you're still going to get the parabola in, say, the yz plane or the xz plane. So let's take a look. Okay, and what this is called is a elliptic paraboloid. Sometimes you'll just say paraboloid. A lot of times people just say paraboloid. Okay, and in fact, if we get rid of the over 4, then you definitely say paraboloid. And there's a paraboloid. Okay. Some people call it a bowl because that's what it looks like. It's great for holding like soup. Y'all agree? Or water. Okay, so it's good for that. It's a tank. Okay, it's an elliptic paraboloid. Notice in this example, if I slice it parallel to the xy plane, I get a circle. Okay, and by the way, it could be an ellipse if I divide it by something. But if instead of slice it parallel to the xy plane, if I slice it parallel to the, say, xz plane, then I get a parabola. So we call that an elliptic paraboloid. Any questions on that? Okay, now what if I take away the 1 and make that a 0? You think that's going to change anything? Is that just going to shift it? Okay, should we check? Okay, so that just shifted it. Do you see that? What if I put the square back in the z? So what we're doing is we're playing around with all of these guys. Is that going to change anything? The hint is you've known this shape since you were probably 3 years old, maybe 2 years old. You even knew the name of this shape. That's a hint before I hit enter. Okay, especially in the summertime, that's your hint. Okay, that's a cone. I'm sure you all had ice cream cones, right? So that's a cone, and it turns out in math, a cone is symmetric about the plane. So notice there's a top cone and a bottom cone. We still call that a cone. Okay. Now, do you remember there was something called conic sections? And
Yes.
that's because, yeah, that's because if you take a cone and you slice it, then you get you get an ellipse, you can get a parabola, you can get a hyperbola. So that all comes from kind of slicing it in different directions. I'm not going to get into involved in the mathematical details of that, but that's one of the cool things about a cone is I can slice and get stuff. So if you slice it vertically, you get a parabola. That's an example. If you slice it horizontally, you get a circle. Okay, and then if you skew slice it, you can get an ellipse or hyperbola depending on how you slice. So any questions on the cone? So lots and lots and lots of different shapes that you can get. And notice that all of these they don't have any powers higher than 2. They don't have any funky things like sines or cosines or e to the x's. They're all quadratics. But quadratic is in 2 dimensions. So let me give you a quick little definition before we go. Okay, and by the way, I've gone through all of these, but now I want to define all of them at once. And that is a quadric surface. Is a surface formed by the equation. And now what we need to do is we need to look at this and say, what are all the different things that can happen that we're allowed to do that I was doing? So I'm not allowed a cube, I'm not allowed 1 over x, I'm not allowed e to the x or sine of x. I just need powers, and they could be 1 or less, 2 or less. So I can have, and let's do an equation. There we go. A x squared plus b y squared. And a and b, the a and b can be positive or negative, and we've seen that makes a big difference. Plus c z squared plus d xy plus e xz plus f yz plus g x plus h y, these get long, plus I z plus j is equal to 0. So they're pretty complex. So a couple things to note, A, B, and C. First thing to note, this D, E, and F, in our class, it'll always be 0. Okay, the only way to handle when they're not 0 is to take linear algebra, and then you'll learn how to deal with it. But we're not doing it in our class. So those are always going to be 0. So if those are 0, A, B, and C will tell you what kind of quadric it is. All those different ones that I was showing you, hyperboloids of one sheet, and ellipsoids, and all this stuff. And G, H, and I will tell you shifting from the origin. So that's a complete the square kind of thing. And J, as long as J is not 0, okay, along with the shifting stuff, then it's just a shift also. And that is the definition of a quadratic surface. You take this, you could pop it into CalcPlot 3D, and it'll be a quadratic surface. It'll be one of the things I showed you. Okay. The only other thing you could have, which I didn't show you, is nothing. And that would be something like x squared plus y squared plus z squared plus 1 equals 0. And that's the empty set. And that's so boring, I didn't show it to you. So we're out of time. Okay. But what I will do, as always, let's stop share. I'm going to stop the recording.